Assalamualaikum warahmatullahi wabarakatuh. So we are from Group 3, BMM 2263, Advanced Fluid Mechanic. So today we're gonna present our project, which is mini water pump. So Assalamualaikum warahmatullahi wabarakatuh. My name is Muhammad Firdaus. So we are from Group 3. So today we're gonna present our project, which is mini water pump project. So as you can see here, this is our water pump, mini water pump. So this is the suction pipe, this is the delivery pipe, this is the DC motor, this is our pump, and as you can see here, this is our electric component, which is have a switch and battery.
Right, so let's move on to the setup for this water pump first. As you can see here, this is a 600 milliliter water bottle, and I'll fill this cup, I'll fill this mug with 600 milliliter water, which equivalent to 0.0006 meter cube. So for this elevation, we have measured the elevation of this head static is equals to 0.22 meter. So let's start our water pump, but first we need to fill this water pump with water. So as you can see here that our water pump is functioning very well. Okay, so that's all from us. Thank you very much.
So this is our team member. My name is Muhammad Firdaus bin Sudi, MA 24127. This is my teammate Muhammad Fatih Fayed bin Anwar, MA 24124, Muhammad Rajauddin bin Ramli, MA 24125, Shivesh anak lelaki Ramesh, MA 24120. Okay, so right now we move to the introduction. So this project focused on the custom design, sustainable fabrication, and performance testing of a mini centrifugal water pump, applying the core turbo machinery principle learned in Chapter 4 of Advanced Fluid Mechanics. Moving completely away from ready-made commercial kits, the prototype features a custom housing casing and an internal rotating metal impeller that actively incorporate both an inlet suction pipe and outlet delivery pipe to maintain continuously fluid flow. Powered by a 12-volt DC motor driven by two 9-volt wires in parallel, the spinning impeller blades accelerate the water radially outward, creating a low-pressure vacuum at the pump eye to continuously draw fluid through the suction tube while increasing its pressure inside the casing to overcome dynamic piping, friction losses, and elevation change according to extended Bernoulli equation. So, goals strictly around United Nations Sustainable Development Goal 12, SDD 12, which is responsible consumption and production. This project implements an environmentally friendly, zero virgin plastic circular framework by fabricating all core structural components entirely from post-consumer municipal waste such as discarded body spray, canister, and plastic bottle cap, directly supporting landfill waste reduction and material reuse in engineering design. So we have the four main objectives in this project. The first one is to design and innovate a custom mini centrifugal water pump system. The second one is to fabricate a functional prototype using 100% recyclable materials. The third one is to model and evaluate hydraulic performance via velocity and power calculation. And the last one is to analyze experimental flow behavior, system losses, and efficiency.
So for the next part, this is our best material selection. First, we have cable connector, silicon tube, battery holder, battery, switch, DC dynamic motor, impeller, and mosaic. And we also have a bottle cap, solder, hot glue gun, masking tape, super glue, concrete, bottle coolant.
Okay, so right now we move to the design concept. So the design concept focus on creating a fully functional small-scale centrifugal pump built completely from scratch using everyday repurposed items. So this directly support the SDD-12, which is responsible consumption and production by practicing waste reduction and recycling. So as you can see here in the picture, so we have the housing and the piping. So the body, we use a common plastic bottle cap, repurposed to act as the main pump body casing. So this hold the water and direct its flow. So the second one, the seal. So to close the open side of the bottle cap, a section cut from plastic bottle coolant container is glued over it, so this create a closed chamber. And for the pipes, we use a silicone tubes are attached to serve as the intake suction pipe and outlet delivery pipe. So the airtight concept is to make sure the pump can successfully suck and push water without losing pressure or leaking. So the joints are sealed tight using super glue and a silicone tube lining. This create a completely airtight chamber. Okay, so for the custom impeller, for the blades, is the impeller is custom cut from scrap metal to fit perfectly inside the bottle cap, with just a tiny bit of clearance. So for the connection, is a hole is melted into the center of the bottle cap using a solder iron. So the drive shaft of the DC dynamic motor is pushed through, and the custom impeller is glued permanently to the shaft using a hot glue gun. So this ensures that when the motor spins, the blade spin right along with it without slipping. Okay, so right now we explain. I will explain the electric component. So for the circuit to easily operate the pump, we put a simple electrical circuit. So the cable connector link the DC dynamic motor and on off switch and a battery holder together. So for the power source, the system is powered by two 9-volt batteries inside the holder. So this provide a portable, reliable power source to drive the mechanical rotation of the motor. So for the base, during testing, high speed spinning causes vibration. So to keep the pump stable and protect the airtight seal, the battery holder and pump are taped down securely with a masking tape onto a heavy mosaic panel structural surface. So an abrasive coarse grit layer is added to testing area to ensure the assembly stays firmly in place during active fluid data collection. So right now I will explain about operating principle of this water pump. So the first is the creating the suck, which is the pump eye. So when you turn on the switch, power from the two 9-volt batteries travels through the wires to start the DC motor. So the motor spins the impeller inside the bottle cap at a very high speed. As the blade spin, they throw the water inside the cap outward. So this create an empty low pressure space right at the center hole, which act like a vacuum sucking water up from your reservoir through the inlet selection silicone tube. So for the second one is the throwing the water centrifugal force. So once the water enters the center of the spinning impeller, the custom metal blades grab the water molecule and spin them around. So this rapid spinning use a centrifugal force. So to throw the water outward toward the inner walls of the bottle cap. So the third one is the turning speed into a pressure. So as the water is thrown against the round walls of the bottle cap, it slows down slightly because the space inside the housing change. So according to the Bernoulli equation, when a fluid slows down in a controlled space, its kinetic energy transforms into a static pressure. This pressure will up force the water to find the only exit available. So the site discharge port. So and the last one is the keeping the flow airtight. So for this entire process to work continuously and smoothly, the system must be completely airtight. So it means there is no air allowed in this pump. So the bottle, coolant, plastic cover, silicon tube, super glue and hot glue gun keep air from entering the chamber because no air can leak in. The pump maintains a perfect seal, pushing a steady pressurized stream of water out through the delivery silicon tube. So the masking tape, heavy mosaic panel, and coarse grid surface keep everything stable. So vibration do not break this airtight seal during testing.
Assalamualaikum warahmatullahi wabarakatuh and good evening everyone. My name is Muhammad Fatih Faid bin Anwar and my matrix number is MA24124. So let's move on to the design calculations. As shown in this slide, these are the formulas that we are going to use in our calculations, which included the total head formula, the major friction losses HF, and minor losses HM. Besides, we also provide some of the important values that we have measured, which including the diameter, suction length, and the delivery length of the pipe, and also the head static and the flow rate of our water pump. Okay, so this is our calculations. As shown in the first picture, we are going to calculate the head estimation, but first we need to find the velocity from the derivation of flow rate formulas. Q equals to area times velocity, which the area we can find the area from the diameter value that we provided from the previous slide. And after that, we can proceed to find the Reynolds number, which we are going to use the formula of Reynolds number equals to density times with the velocity times with the diameter of the pipe and divided by the viscosity. So since the Reynolds number is greater than 2300, then we assume that this flow is a transitional flow. Then we are going to use the friction factor formula, which is friction factor equals to 0.316 over with Reynolds number to the power of 0.25, and then we will get the friction factor value. So for the second picture, that we can calculate the head loss by using the head losses major friction losses that we have provided from the previous slide, and we also can calculate the minor losses by assuming that the standard pipe entrance with 0.5 and the sharp exit with 1.0, and we finally can calculate the total head estimation by sum up all the values of head static, um, major friction losses and the minor losses, and then we'll get the head estimation value. So for the last picture, this is the calculation for the velocity and power calculations. So to calculate the velocity, it is very simple that we have calculated the velocity from the first picture. It's basically the same. So to calculate the hydraulic power, pH, we are going to use the formula of pH equals to density times with the gravitational constant times with the flow rate Q and times with the total heat H. And then we'll get the hydraulic power. So for the electrical power, we are going to use the formula of P in, power in equals to voltage times with the current. So in this case, we are using the circuit that is connected parallel. So the voltage is going to be 9 volt for each battery, and then times with the 0.5 ampere current that we have measured using the multimeter. So to calculate the efficiency, it is very simple that we just divided the values of the hydraulic power with the electrical power and then times it with 100, and then for this one we'll get the efficiency. Its efficiency is 0.88%. All right, and in this slide we have provided a table for the element analysis performance, where in scenario 1 we have changed the discharge time into 114.46 seconds. For scenario 2, it's remained the same as our previous calculations, with the value of discharge time 57.23 seconds. While for the scenario 3, with the highest flow rate, that we have reduced the discharge time into 28.62 seconds. As you can see, that for the scenario 1 with the lowest efficiency with 0.3%, followed by scenario 2 with moderate efficiency with 0.88%, as we have uh, calculated from the previous calculation, and for the scenario 3 with the highest efficiency with 3.37% of efficiency.
So for the next part, which is sustainability aspects, including material selection. First, we have material selection. It is lightweight and low-cost material use, and plastic cap used as a pump casing, flexible plastic tubing for water flow, and foam board uses as mounting base, and components can be reused or recycled, and minimal material consumption and waste generation. And for the second, energy efficiency, which is operate using a 9-volt battery, low electrical power consumption, simple DC motor reduce energy and losses, and potential for integration with solar energy system. And the last one, which is environmental impact, it is compact and energy efficient design, promotes responsible use of materials, suitable for small-scale water transfer application, and can support rainwater harvesting and irrigation system. So for the next part is SDG relevance. So there is only one SDG, which is SDG 12. It is responsible consumption and production. It is use reusable and recyclable materials and reduce material waste through simple design.
Hello, my name is Shivesh and my matrix number is MA24120. Today I will be presenting the discussion section of our mini water pump project. For this part, I will discuss first three things first. First is about the performance of the pump. Second is the challenges we encountered during the fabrication and also the testing. And finally, the lessons and observation we gained from this project. Let's start with the pump. Based on our testing results, the mini water pump was able to successfully transfer the water from the source container, which is we use a bottle container, and this shows that the pump was functioning as intended and that the impeller was able to generate enough pressure different to the move water continuously. Looking at the results, we can see that as the discharge time decreased, the flow rate increased. When the flow rate is increased, the fluid velocity, total head, and the hydraulic power also increased. This trend is expected because a larger amount of water is being transported through the system in a short period of time. As a result, the pump transfers more energy to the fluid. Another observation is the pump efficiency, which is the efficiency increased from 0 to 30% in the low flow condition to the 3.37% in the high flow condition. Although these values are quite low compared to the commercial pumps, but we have to remember that this project was built using a simple recycled material and a small DC motor. Therefore, achieving a stable and continuous water flow was already a positive result for our design. So now moving on the second part, which is the challenges we encountered during the project. So one of the main problems we faced was water leakage around the tubing connection and the pump casing. During the first few tests, some water escaped through small gaps, which reduced the suction effect and affected the pump performance. To solve this issue, we apply like hot glue or super glue around the joints to improve the sealing. After making this adjustment, the leakage was greatly reduced and the pump was operated even better. So another challenge involved the impeller alignment, which is the blade inside rotating. So initially the impeller was slightly touching the inner wall of the casing. We noticed this because the motor produced vibration and the water flow was not stable. After several adjustments, we managed to position the impeller correctly so that it could rotate freely without contacting the casing. This improved the smoothness of operation and helped increase the water flow. We also experienced another thing, which was air bubble trap inside the tubing. These air pockets affected the suction capability of the pump. To overcome this issue, we primed the pump before testing and ensured that the tubing was completely filled with water. So finally, I would like to share some lessons and observation from this project. So one thing we learned from this project is even a small thing such as sealing, tubing connection, and proper impeller positioning can have a significant effect on the pump performance. So before doing this project, we mainly focus on calculation. However, during the fabrication process, we realized that practical factors are just as important as theoretical calculation. This project also helped us to understand how the connection learned in advanced fluid mechanics applies in a real engineering system. Concepts such as flow rate, fluid velocity, head loss, hydraulic power, and efficiency. So overall, this project gave us valuable hands-on experience in design, fabrication, testing, and performance evaluation. It allowed us to connect classroom theory with real engineering practice. Thank you. That concludes my discussion section. All right, for the conclusion, our mini water pump project was successfully designed, fabricated, and tested using simple recycled materials and a DC motor. So, through this project, we were able to demonstrate the basic operating principle of a centrifugal pump, where mechanical energy from the motor is converted to the hydraulic energy to the water through the system. The experimental result shows that the pump was capable of producing continuous water flow, and we observed that the higher flow rates resulted in higher velocity, total heat, and high power output. So, in addition, this project allowed us to apply important fluid mechanics concepts such as flow rate, head loss, Reynolds number, hydraulic power, and pump efficiency in a practical engineering application. So, from a sustainability perspective, the use of recycled materials such as bottle caps and plastic component helps reduce waste while supporting the Sustainable Development Goal 12, which focuses mainly on consumption and production. So, overall, this project provided valuable hands-on experience in engineering design, fabrication, testing, and performance evaluation. It also helped us understand how theoretical concepts learned from the class can be applied to the solve real engineering problems. Thank you so much.